Welcome, developers, to a crucial discussion on managing concurrent access in your applications. Today, we're diving deep into synchronization primitives, specifically comparing Spinlocks and Mutexes. Understanding these mechanisms is fundamental for building robust, high-performance systems. By the end of this lesson, you will be equipped to define critical sections and race conditions, understanding why they necessitate synchronization. You'll then understand the mechanics of Spinlocks, appreciating their unique approach to resource locking. Following that, we'll explore the mechanics of Mutexes, contrasting their behavior with Spinlocks. Finally, and most importantly, you'll learn to choose the appropriate primitive for different scenarios, ensuring you make informed design decisions in your projects. Let's get started. Before we compare Spinlocks and Mutexes, let's ensure we're all on the same page regarding the problem they solve: critical sections and race conditions. A critical section is simply a segment of code that accesses shared resources. Think of it as a guarded room where only one person should be at a time to prevent chaos. When multiple threads or processes try to access and modify this shared resource simultaneously, that's when trouble can start. If the final outcome depends on the unpredictable timing of how these threads execute, you've got a race condition. Imagine two threads trying to increment a counter at the exact same moment. Without proper synchronization, you might lose an update, leading to incorrect results. That's why managing these critical sections is, well, critical. Now, let's introduce Spinlocks. A spinlock is a basic synchronization primitive where a thread attempting to acquire a lock that's already held simply waits in a loop, continuously checking if the lock has become available. This is known as busy waiting. The main advantage here is its simplicity and low overhead when contention is minimal or the critical section is extremely short. Since the thread doesn't yield the CPU, it avoids the expensive operation of a context switch. However, this efficiency comes at a cost. If the critical section is long or contention is high, the busy waiting thread will consume CPU cycles pointlessly, leading to high CPU utilization without doing any productive work. It's like standing impatiently at a door, constantly rattling the handle, rather than sitting down to wait. In contrast to Spinlocks, we have Mutexes. When a thread tries to acquire a mutex that's already locked, it doesn't busy wait. Instead, the operating system puts the thread to sleep and moves it off the CPU, scheduling another thread to run. When the lock becomes available, the sleeping thread is woken up and rescheduled. This makes mutexes ideal for longer critical sections or situations where contention is expected to be high. The sleeping thread doesn't waste CPU cycles. However, this benefit comes with an overhead. The act of petting a thread to sleep and waking it up involves a context switch, which is a relatively expensive operation for the CPU. So while mutexes offer low CPU utilization during contention, their performance can suffer if critical sections are too short, making the context switch overhead disproportionately large. So when do you choose which primitive? The decision largely boils down to the expected length of the critical section and the level of contention. You should lean towards Spinlocks for minimal contention and very short critical sections, often measured in just a few CPU instructions. Think of low-level kernel operations where every cycle counts. Conversely, mutexes are generally preferred for moderate to high contention and longer critical sections, where the cost of a context switch is less than the cost of busy waiting. Always consider the context switching cost versus the busy waiting cost for your specific scenario. Remember, the goal is to minimize wasted CPU cycles and maximize throughput. By now, you should be able to define critical sections, understand the mechanics of both Spinlocks and Mutexes, and confidently choose between them. To test your understanding, when would you choose a Spinlock over a Mutex for an I/O operation?